This is part 4 of the Module 8 lecture. Now, in this section, we're going to look at specific examples to see how we can test a population mean when the population standard deviation is unknown, and this corresponds to section 9.3 in your textbook. You may recognize this diagram. It's the same diagram that I show you at the beginning of Chapter 8 in Module 7. And as in the previous case, I'm not going to discuss the situation where the population standard deviation is known. There's no point. That's not a realistic situation. So we're going to focus on the realistic situation that the population standard deviation is not known. And we're going to focus only in these two cases, when we are taking a sample from a normal population and when we're taking a sample from some population that is unknown or is not normal, but the sample size is very large. So for both of these cases, the sampling distribution of the mean is normal, and as we saw in when we were calculating confidence intervals, we're going to use the t-distribution. All right, so now we're going to follow this 5-step procedure to test the hypothesis. So we're going to translate the practical problem, which is given to us, into the statistical problem. Once we do that, we do the statistical analysis. Then we reach our statistical conclusion, and then we translate that statistical conclusion into a practical conclusion. All right, let's do that. This is, you may remember, this is the first example that I showed you earlier when we were talking about the null and alternative hypothesis. So a concern in today's health insurance is the amount of deductible that people with employer-provided health coverage pay. This organization, the Peterson Kaiser Health System Tracker, claims that the average amount of deductible paid in 2015 is $1,077. So in a study, 78 individuals with employer-provided health coverage were selected at random to evaluate the amount of deductible they pay in 2016. And the sample mean and the sample standard deviation, so the deductible pay is $1,168 and $369 respectively. Now, based on these sample results, we want to determine at a significance level of 0.05 if the true mean of the deductible pay in 2016 is higher than the average amount paid in 2015. Now, I underline a few things here to help you notice that the amount of deductible, that's the money paid, is a continuous random variable. And we're dealing with the mean of a population. And I'm highlighting the significance level. And then the true mean, that's another indication that this is the parameter we're dealing with. And this higher than, that's telling you that this is the alternative hypothesis. All right, so all this information, the first step when you start solving this problem, summarize the information that are given to you in the problem. So the very first thing you notice is this 1,077. So this is the assumed value of the population mean, because we want to compare 2015 to 2016. So mu sub 0 is 1,077. The sample size is 78. The sample mean is 1,168. The sample standard deviation is 369. And alpha, the significance level, is 0.05. All right, step 1, establish the hypothesis and the direction of the test and the significance level. All right, in here, we are looking to see if the average amount of deductible pay in 2016 is larger than 1,077, which is the value that was paid in 2015. So under the null hypothesis, we're going to assume that the amount paid, the average of the amount paid, is the same or maybe smaller from 2015 to 2016. Now, because of the inequality in the alternative hypothesis, then we're looking for values larger, values of the mean larger than 1,077 to support the alternative hypothesis. So that tells us that the direction of the test is a right tail test, and the significance level well, is given to us as 0.05. All right, the next step is the selection of the distribution that we're going to use. So this is a random sample, so that implies independent observations. The sample size is 78, much larger than 30, so we can safely assume that the sampling distribution of the mean is normal. The population standard deviation is not given, and of course we're going to replace it with the sample standard deviation, which is known. And then because of those three characteristics, then we will use the t-distribution with 77 degrees of freedom, which is the sample size minus 1. So since we're using the t-distribution, this is the definition of the test statistic. So what we do then is replace the known values into this equation, and we carry out the calculation. So the observed mean is 1,168. The value of the mean under the null hypothesis is 1,077. The standard deviation is 369, and the sample size is 78. So when you carry out this calculation, you will obtain 2.178. So this is the calculated value of the test statistic, or t observed. All right. So the fourth step is finding the critical value or finding the p-value. So we're going to do both. Let's start with the critical value approach. So here we're going to use table 5 with an alpha of 0.05, which is given to us, and the degrees of freedom, which is 77, to find that t critical. Now, the table, as you can see, does not contain a row for 77 degrees of freedom. So we're going to use the closest row in degrees of freedom, which is 75. So that's the row that we're going to use in table 5. So find that row on your table 5, and then look at the top and find the probability of 0.05, and then at the intersection of the column with the probability of 0.05 and the degrees of freedom of 75, then you find that the t-value is 1.665. And because the table gives you probabilities to the right, so then you know that this is the critical value that we're looking for. So this value of 1.665 identifies the rejection region, which is any value of the test statistic bigger than the TC of 1.665. So, and that's what I'm explaining in these two bullets. Also, I'm giving you the Excel equation if you like to use it. You can just type this in, equal to this, to TIMV and parentheses and these numbers, close it, press enter, and that will give you the exact T critical value, which is this, 1.66489, which is very close to the value we get from the table. All right, so now we know where the rejection region is, and is defined for values larger than 1.665. All right, the p-value approach is the alternative approach, and we also want to look at that. So in table 5, on the row for degrees of freedom of 75, we cannot use the degrees of freedom of 77. There's not such a row, so we're going to use that row with 75 degrees of freedom. And you can see that the observed value of the test statistic is 2.178, which is between two values, the two values in the table on the row of 75, which is 1.992 and 2.377. So remember, we're trying to find this probability, the probability to the right of the t observed value, the value that we calculated. So we're looking for that probability. Fortunately, table 5 does not give you every possible probability. So the best we can do is to find within which values the calculated value of the test statistic is, and that will give us an idea of what is the magnitude of the p-value. So as I said, if you go to the row of 75 degrees of freedom, then you find the closest values to this t observed are 1.992 and 2.377. If you go up to the top of the table, you will see that 1.992 is under the column for a probability of 0.025, and 2.377 is under the column of a probability of 0.01. That means then that the p-value is between 0.025 and 0.01. Now you can use this formula to find the exact p-value, and you see that the exact p-value is 0.01623. Unfortunately, table 5 is not useful to find the exact p-value, but we can find give us an idea from the table. All right, so now we found the p-value, and we found the critical value that determines a rejection region. All right, so in part 5, we make a decision about the null hypothesis. So if we decide to use the critical value approach, we compare the calculated value of the test statistic with the critical value. And you see that the calculated value is larger than the critical value, meaning that the t observed falls in the rejection region. Therefore, we reject the null hypothesis that the mean is 1077 or smaller. So that fact is rejected. Or you can, if you prefer to use the p-value, then you see that the p-value is 0.01623, and that's smaller than 0.05. So because the p-value is smaller than the alpha value, then we reject the null hypothesis. So either case is equivalent to each other. But as I said, if you read any type of paper, any type of published literature on statistical studies, they use the p-value. So the interpretation of rejecting the null hypothesis is that the actual average amount of deductible that people with employer-provided health coverage paid in 2016 is higher than that amount paid in 2015 at a significance level of 0.05. This is very important to quote the significance level, because another researcher using the same data may find a different conclusion if that person decides to use a different significance level. All right, so this is the first example of where we test a hypothesis using both the critical value approach and the p-value approach. So in the next segment, we're going to look at two problems and using exact same procedure, but we have two different situations. All right, we'll stop here, and in the next section, we'll review two more problems.